Welcome to the virtual lab tour of the Wadley Research Group. My name is Jeroen. I'm currently a postdoc in the group, and I'll be taking you to some of the facilities that we use to do intelligent processing of materials and also the testing of these materials. If you have any questions, feel free to reach out to myself or Professor Wadley, and we will gladly give you information on any of these facilities. Thank you so much for watching this virtual lab tour, and I hope you enjoy it.
The first system that we'll look at is the spark plasma sintering machine, where you apply force and current onto a graphite punch and die system, which will rapidly heat it, and it will react to powder together and form a solid and mostly dense puck of material. So we usually start out with research in something like this, where we can just mix powders and then put it in a graphite die such as this. Just put the powder in there, put your punch in it, protect it with a felt wrapping so that the heat does not escape as much during heating. You put that in the hydraulic system right here. You can apply up to about 100 kilonewtons of force. Usually we are in like the area of 40 to 60 MPa, and then you compress it first, and then the current that also comes through the rams will get on it, and that will rapidly heat that graphite die system up to about 200 degrees per minute, and yeah, that can get you quick consolidation, and with that you can do testing of your materials. Now here we have the plasma spray facility, where we can do atmospheric plasma spray, so plasma spray in atmospheric conditions. Now what this does is, here you have a plasma torch made by Praxair, where you create a plasma right in here. You inject powders from either the top or the bottom, which gets then injected into the plasma right here, and then gets shot out at a high speed. It's controlled by a robot, as you can see here, and it can then hit a target such as this. Now, and typically here we make silicon and ytterbium disilicate coatings for environmental barrier coating systems, but we can do multiple things. We can do metals, we can do carbides, all kinds of different materials that are typically made using atmospheric plasma spray. Now, aside from that, we also have a high temperature furnace. I'll show you the inside for that, where we can put our sample on the inside here. For instance, we can put silicon carbide, and then usually we do that using the plug on front, and then the inside can get heated to about 1200 degrees C. Then we also flow argon through these holes down here, or we can also flow a little bit of hydrogen if we want a reducing environment. Then during spraying, we can take out this front piece and spray in here using the robot. Now we usually can spray things on silicon carbide using a setup like this. That is a silicon carbide block on there. We can also spray on metals, but we use silicon carbide for our experimentation in the new materials for airplane turbines. And the powder that is supplied here through these powder feeders. We have 4, so we can do 2 at a time, and we can go up to 4 different powders. So these are stored for different types. So we've got like yttrium disilicate, ytterbium disilicate, silicon, and then a spare one. So actually we'd like to show you a bit more about the inside of that torch, the plasma torch that I just showed you. On the inside you have a cathode, an anode. So when you apply a high current with high voltage, you will actually start to create an arc here, and you can start to ionize the gas that you're flowing. So the gases that we're usually flowing, we have multiple gases. We can flow argon, nitrogen, and helium and hydrogen, and we can flow that into the system. You usually use 2 different kinds of gases. You can have a primary and a secondary gas. So for instance, we use a mixture of argon and hydrogen usually. So when that gets here, it starts to ionize, and then it will shoot out a plasma right there. And that plasma can reach a temperature of about 20,000 kelvins locally. So when your materials are injected right here from the top and the bottom, then it will start to locally melt. You get something that looks somewhat like this. So we'll have a molten exterior and a still solid core, and that will then get shot at your substrate at a high velocity. And that will eventually look like, well, something like this if you're doing cold deposition. So that's when your substrate is at an ambient temperature, so like let's say 25 degrees Celsius. Then when that particle hits your material, you're starting to get rapid cooling. Now this material, because it's shot at a high speed, it will actually form kind of a splat like this. And because you have rapid cooling, you will actually start to get some amorphous material growth. It will not have the time to actually form a crystalline material. Then when this happens multiple times, and eventually you get a layer of materials that can be partially porous and also semi-amorphous or semi-crystalline. And that is something that you don't really want, because once you heat it up again, it will start to crystallize and it will start to transform. On the other hand, when you do it on a heated substrate, you will not have that rapid cooling, and instead you're going to start growing a crystalline material. And when that grows, then this actually, all these spores that you see here, because the rest is still molten, it might actually creep in there, and you can fill up these pores until you get a fully crystalline, or at least mostly crystalline material. We also have our directed vapor deposition system. And right now Chris is depositing refractory metals with that. He'll later show you a bit on the inside of the DVD. So with the DVD, you use an electron beam gun to evaporate source material, so you can actually see the source materials of titanium and then tantalum being evaporated here. So we can keep an eye on what's happening. And so we can in situ decide where our electron beam hits it with how much power, and as a result, it's a bit bright. We actually see our source material getting evaporated down there onto the substrate up there. Let's actually see if this works. Yes. We see our substrate getting heated up to about 1200 degrees C up there. And then the blue, what you see down there, is actually evaporation of the material.
So here's the interior of the DVD chamber. So the electron gun, it comes through this viewport right here. Get some more brightness in there. So right here. And then it's aimed directly at our crucible, which is situated down here. This is our copper crucible. And in there we have two source materials situated, which we have a tantalum source material right here and a titanium source material right there. We're trying to do with co-evaporation. And then we have a ring right here, and this is where we flow our inert gas through to carry our vapor up to our substrate. So our substrate is situated right here, and behind that is a block of boron nitride that has a tungsten heater in it, so that we can radiatively heat the substrate from behind. And then if we pan back, we see that this is a hollow cathode setup. Right here, there's actually 4 of them. There's one here, and then 2 on the other side. And this is set up for in case we wanted to use plasma systems for our deposition. Also in the interior of this chamber, we have our copper cold traps. So we run liquid nitrogen through this line. And then what that does is this gets super cold and allows more gas in the background to condensate onto these copper fingers, and then it reduces the background pressure of the chamber. And that's the quick run through of the interior of the DVD.
Now, not only can we just deposit materials or process them using the SPS, we can also process them using a high temperature furnace, or we can even test materials in a furnace like this. Now, this furnace in particular has a maximum temperature of 3000 degrees Celsius. And the reason that it can go up that high is because this is all graphite. So it's a graphite furnace that you need to use argon or a vacuum with. Because if you use oxygen, you can of course imagine that this whole inside would burn up to a crisp and just form CO gas. So yeah, you can test it using a furnace like this. We also have a standard tube furnace where you can use air up to about 1800 degrees C. You can also use in a controlled environment if you want to. And then we also have this thermal cycling furnace where you can insert water. So we have jugs of water that get transported using a peristaltic pump and then get inserted into the furnace right here. And then samples that are hung on the bottom using a platinum wire then get cycled. The furnace can actually move from this position all the way down. Your sample stays at the same height, and then it goes from the bottom all the way up to the middle of the furnace where it's hottest, so up to a maximum of 700 degrees C, and that is done to test coatings for environmental barrier coatings for silicon carbide based components. Aside from using a typical furnace, we also have another big testing facility. This is called the Simulated Engine Testing Facility. We also call it the LSL, and it stands for Laser, Steam, and Load. So what we can do with this is when we have made coatings, we can actually test them in all three major categories, that being heat, so at high temperature, environment, steam or air, and under loading, so using a force. So basically you can mount your specimen inside of this chamber. Now typically engine coatings get also cooled, or engine components get cooled from the backside, so that's what you see in the back right there. Then from the front you can have steam come in, and you can also further cool it with air. On the sides you can measure temperature, and then yeah, you can heat it with the laser from the front. And the benefit of doing it this way is that you can simulate the actual conditions in an engine. You can also put this at a high pressure, I believe up to 12 atmospheres. You can heat your steam up to about 1,000 degrees Celsius using this giant furnace, and then you can also again cool it from the back so that you can create a thermal gradient. Now this system has just been completed in 2020, and with this we can start testing coatings in a more dynamic environment.